that in the electrical world, and you have to do that in the mechanical world. And ohms and amps and watts and kilowatts and all that is one thing that we measure, okay? But then on the other side, we also measure diameter, lengths, inside, outside diameter, parallelism, perpendicularity, all of those features that make a product work. I started out in this business when I was very, very young, by your age, okay? Well, tell me 36, so. Measurement started in antiquity. You can't make anything unless you know what you made. You can't make anything unless you've measured it. Even though you may think you have it, your professor measures your performance by giving you an A or a B or whatever. There's a measurement. You're driving your car and you're staying so far away from the guy in front of you. That's a measurement, but it's all being done, calculated in your own mind. But they're all measurements. I was watching something on TV on Discovery, because I don't watch anything but Science Channel, because there's something wrong with it. And they had this guy who was going around the world looking at various construction sites in antiquity. And what he was watching and looking at was the commonality between the structure, how they were able to build these buildings block on block without mortar. And then there was absolutely no space in between the stones. How did they do that 5,000 years ago? Nobody knows, but we can think about how they did it. Because those people 5,000 years ago, maybe they didn't have the tools, but they still had the brains. They weren't stupid. They just didn't have the tools, okay? So it's that evolution, starting then, where we now get the tools and more tools in order for us to become more proficient and in many ways in life, besides manufacturing. Sticking with mechanical measurement, we know what the foot, everybody's known what a foot, what we call it 12 inches. But where'd the foot come from? It used to be the length of the foot of the king. Technically, that's what it was. Of course, you can have a big king, small king, and the foot can change. And obviously, that doesn't make for good measurement, because you must have a standard. So one of the first standards ever made was the cubit. You might have heard the word cubit in the Bible, where the ark was built with so many cubits in this direction. And the cubit has been used by the Greeks, by the Egyptians, and there exists today bars, ancient bars, that this particular civilization called the cubit. There's another one over here that different length, but they called it a cubit. The cubit was the distance from your finger to your elbow. Now the distance from my finger to my elbow and the distance from his finger and his elbow, all that's different. We had to get away from that. We had to get away from not having a standard. We have to have standards, because otherwise nobody's going to know what we're doing. How do they make those surfaces so flat that they just went together with that? And we say, oh my goodness, some people say it was ancient aliens. This guy was trying to tell me he was an ancient alien. I think he was an ancient alien. But they didn't think about was these people, not being stupid, realized that they had to lap the surface. And if they lapped the surface, they took a stone and some fine sand and some water, all right, maybe some other materials they might have had, and they constantly did this until the surface became very smooth and very flat. And then they put it together. And they said, oh, look how wonderfully they fit. Gee, it must be an ancient alien. No, they knew enough that they could work materials to be able to make them flat and to be able to make them sit together and stay together for thousands and thousands of years. Are they stupid? So we started with the foot. We have measurements in weights, pounds and ounces. By the way, probably the only, I think there are 2 or 3 countries in the world that use the inch measurement for dimensional measurement. The United States being one of them, and a couple of other nondescript countries. So we're the only, kind of stand alone as a nation that hasn't gone to the metric system, which is a much easier, logical system, but we're into it now. But if you're in medicine, everything's a metric. Okay. Certain industries, everything's a measure. But when it comes to the mechanics in this country, we're still in the inch world. There was a man named Henry Ford. Henry Ford started the Ford Motor Company. Now, lots of people thought that Ford invented the car. He didn't invent the car. He invented the assembly line and how things went together to create cars in production environments. Because they used to be produced a team, 4 or 5 people, and they started with a chassis, and then 5, 6 people would get together and they put together a car. It was all handmade and hand fit, and well, you certainly couldn't create production. You couldn't create millions of cars for the people in America if you're doing them one by one. So he invented the assembly line, and that sparked a tremendous increase of necessity for standardization and measurement. Why? Because if you're making the bumper in Cincinnati, and you're making the bolts for it in Indiana, when you get it in Detroit, you better go to Gilly. So you have to know what you're building with a standard of some kind. And you have to know what you're building with a standard of some kind. So now we need standards. Well, what's a standard? Well, a cubic was one of the standards, okay? As you said, there was variation in what they were in the various nations. But he reached out to a man in Sweden named Carl Edward Johansson. And Johansson he was a gun maker. And he had put together the concept that artisans back then all had their little standards when they built things that they used to compare in order to build a watch or in order to build a gun. They had their own standards. But he was able to put together a series of blocks. Can you show a picture of a cake block? Blocks, and all the things that get measured have to go back to these blocks. Because you have to measure your parts with a gauge that has to be set to something that you know is close to perfect. And that thing, in this case, has to go to the National Institute of Standards and Technology in Washington, D.C., or a laboratory that connects to them. And they have to certify that the blocks are right. And if the blocks are right, your gauge is right. And if your gauge is right, your measurement is right. And if your measurement is right, your product is going to be good. There are different kinds of ways of approaching measurement, inspection, quality control. All these words are sometimes interchanged. Quality control, measurement, inspection. How is a part first thought? You take a drone. You got drones. So somebody sits back and says, "I'd like to make a drone." All right, Charlie Drone. I think that was his name. The guy who invented it. It's Charlie Drone. Believe me, look it up. She's like, she the only one who gets it. So I don't know where the word drone comes from. But anyway, I guess from a bee or something. But that product, that item, has to be designed, usually today, on what? Computer-aided design, computer-aided system that designs each and every components of that. Then, somewhere along the line, it's going to go into a manufacturing process. It could be turned on a lathe, it could be milled, it could be stamped, it could be formed, depending upon the shape and what is necessary in order to assemble it. Each one of these items has a tolerance. Tolerance. Your grades have a tolerance. You can't get higher than A, and you better not get lower than F, right? There's a tolerance. At some point, your mother and father are going to kick you out of this university because you passed the tolerance. Okay? Come home at 11 o'clock, and you come home at 12, you passed the tolerance. Okay? So everything that is manufactured has a tolerance. Usually it has a plus or minus tolerance. In other words, it can be as big as this, as small as that, but no bigger than smaller than this, the other thing. Why? Because if you pass those parameters, if the shafts on those drones are too fat, too large, you're not going to get the propeller on, right? If the propeller hole is too small, you're not going to get the propeller on. So I call them gazinders. This goes into that. And when you have this goes into that, those things have to be precisely formed and held to specific tolerances. For example, if you have a hole that you're drilling a hole. You're drilling a hole, you don't tolerance the hole in 1 inch hole. Let's just take a 1 inch. You don't tolerance the hole 1 inch minus 5 plus 5. Whatever it was, maybe 5 thousandths, let's use that thing. Because you don't want the hole that gets, when the hole gets machined and the drill wears, what happens? The hole gets smaller. So you don't want to start out with a dimension that's on the small side. You can't say something, I want 1 inch minus the dimension. You always have to tolerance that, I want a little bit bigger, because as my tool wears, I'm going to run back to what? Nominal size, the size that I'm looking for, the size that was designed, the size that the designer wants. But this that goes into that. Everybody understand a gazinda? A gazinda, this goes into that. It's one of my words. You can write it down if you like. But if you think about it, assembly, which Henry Ford invented, was so important to have the gazindas right. Otherwise, you're not going to get the tire on the hub, right? Not going to get the steering wheel on the post. It just isn't happening. So there are types of measurement. There is attributes, and there's variables. An attribute is, we use it in our common world, John is tall. We don't give him a dimension. We say 6'3", John is tall. By attribute, he is tall. Margaret is pretty, right? What is pretty? Your eyes are pretty, my eyes are pretty. Okay. So these are attributes, these are things that we see subjectively. And subjective measurements aren't so good. They can help us, but we need to have objectivity. And in order to have objectivity, we have to get specific understanding of dimensions. And like I say, this applies to your electrical as it applies to mechanical. Everything has a tolerance. You can't have something say, well, I'm going to build this and it's going to be a 20 amps plus or minus 60 amps. That can't happen, right? It has to have some kind of parameters. And those parameters have to be adhered to. Who makes those parameters? A design engineer on a CAD system. In today's world, before it was draftsman. You don't even know what a draftsman is. Anybody know who Frank Sinatra is? Oh, geez, what do you know? I'm shocked.
Abbott and Costello?
Abbott and Costello, no, let's not go too far. So, the variables aspect of things is designed by a CAD computer. The CAD system says, I want this shaft on that drone to be 1/4 of an inch, plus nothing, plus 5 thousandths minus nothing. Let's talk about thousands. Let's get some dimensional measurement lingo now, okay? Would you like to do this? Are you excited about this, Will?
Yeah.
Would you rather be home like having coffee or something? I mean, I'd rather be home like having coffee, but I never saw a better looking group. So, we all know what an inch is. Boom. Again, in the United States, we use this system. Okay. This, what do you guys call this? Anybody know what you call it? I heard people say it's 1/10 of an inch. The terminology sound right to you? What's wrong? It's 100 thousandths. Okay. Because this position is the thousandths position. So this is 10 of those. This is 100 thousandths. Of course, that's 200 thousandths. kind of simple. I mean, you guys are in college. You've seen this before. This is 10 thousandths. Oh my goodness, look at this. I wonder where I thought. Is that spell right? This is 1,000ths. If you were in a shop, in a machine shop, nobody would say, "Hey, what do you got there? How much are we off? We're off 5 thousandths." Let's say 5,000. It just as a shortening of the term. So if you heard 5,000, you know what he's meaning. He means five of these little things. How thick is your hair? What's the diameter of your hair? You don't know? Everybody knows. You don't know the diameter of your hair? Oh my goodness. You know yours?
Pretty thick.
Pretty thick. I didn't say your head, I said your hair. All right, so a human hair is about 3 thousandths. So, yeah, 3 thousandths. A human hair is about, some people have thicker hair, thinner hair, 2.5, 4, it's in that range, about 3 thousandths of human hair. So when you say to somebody, "Hey, I want to make this shaft 1 inch plus or minus 3 thousandths, I'm saying I want to make this shaft within a hair. How do you measure that? You don't lay your hair down on it. You have to have tools that read close enough. Let's see some gauges. What indicators are, George? That allow you to make the measurement and see whether it applies to the CAD, right? The CAD, we just had a whole history here lesson, I guess, this week on voting and the government and whatnot. If anybody understands it, raise your hand because I need help. You don't understand it either? Okay. So,
What do you want?
did I? A gauge with indicators. Indicator gauges. Well, upper right. Yeah, that's cool. Okay. You see the thing looks like a pistol? Off to the far right? That tip of that expands to go into a bore. And the more it expands, the indicator is going to indicate what its size is. But how is it set? It was set to a standard. It was set to another standard. It was set to a ring. And that ring was set to an instrument that was traceable to a gauge block that was traceable to where? National Institute of Standards and Technology. The National Institute of Standards and Technology. Now, we have a government. We have a government, believe it or not, all right? And the way the government runs, or supposed to, you have a legislature, and what do? They write the bills, right? They write the bills. I guess there are Senate bills too, but the legislature or the House of Representatives, they write the bills. That's the design group. That in manufacturing would be called computer-aided design. They wish they were that, organized about it, but that's what it is, computer-aided design. So there's the law. This part shall be 1 inch plus or minus 3 thousandths. There's the law. We wrote this down on the CAD package. And therefore we now go to the manufacturing world. It's like there's a lathe in the other room. And we're going to make this on a lathe. And then we're going to measure it. Well, you say, well, you made it. You made it. I made it. Not everything is the way you think it is. You mean you get products that you bought and they always work? You never had to send anything back? You never had a shoe that was a size 9 that didn't fit? Right? So there's variation and there are mistakes. So, once you get into the manufacturing world, you now have, let's start out here with CAD, okay? And we say this stands for computer aided design, right? And then we have CAM. Well, it's still computer aided, but this is manufacturing. Okay? So what happens is the CAD system sends down to the manufacturing world a program, generally, to be able to produce this part, right? In the real world, it can be produced sometimes. But ideally, we want to produce it exactly the way we drew it. But we never will build it exactly the way we do it, because why? If I'm turning this on a lathe, and I have a tool that's going and touching this, and the tool starts to wear, what's going to happen to that shaft? It's going to get smaller, or it's going to get bigger? It's going to get bigger. But it doesn't have to get bigger a lot, because I only have a hair. Right? I'm dealing with a hair. So I better make sure that that tool doesn't wear too fast and start giving me parts that are oversized. You getting that? Does this make sense to you? Well, good, because you explained it to me. It doesn't make any sense to me at all. Listen, this is a very important class because you can never fail it, right? You'll never get an F in this course, right? Because I don't mean anything. This is just to have fun. Are you having fun? Okay. You better be having fun. All right. Computer-aided manufacturing. And then we have computer-aided inspection. Why? 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 Because we have to be able to keep up with the other guys. If we have computer-aided design, we have computer-aided manufacturing, what are we going to do? Stand there with the gauge like this and say, hey, Charlie, it's much too big. How much? Well, I don't know. It looks to me like it's maybe a couple of thousandths off. Oh, yeah? Don't worry. So in today's world, these things are getting integrated. We have machines. Go to a quarter measure machine. We have machines that are automated that can go in and measure with probes. We'll get to that one. That one's rather small. That actually would fit between here and the file cabinet. How big it is, okay? And these machines have probes. They're robots. They're measuring robots, and they go around and they go beep 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 beep, and they're picking up points. And they're picking up those points and they're sending it into design review, and they're sending it into what it's supposed to be, and they're showing the differences. And then they can feed back to the guy who's making the tools, the tooling guy, and they can say, hey, this tool is wearing the part not bigger. So what's he gonna do? He either has to move the tool back more, in more, I should say, get closer, or if it's worn really badly, he has to replace it. But if you're going to have Charlie just sit there thinking about what should I do now, this is not very efficient. Tomorrow's world is to move towards efficiency, and that means that we have to have direct input between what we measure, what we're manufacturing, what we design, and does that circle maintain the circularity, or is there a break? Sometimes what they'll do is they'll take the part, see what's happening to it, take a statistical analysis of the part, and send it back to the computer-aided design people and say, hey, we can't make this. I had a guy say to me, listen, my machines that I got, I can't use all these measurements and have all this feedback because my machines can't make these tolerances. Then I said, well, get out of the business. If you can't make it, then what the heck are you doing? Then you're not a machinist, right? Give the job to somebody else, right? Get a new machine. Oh, management will never go for that. Well, then close the doors. Because your parts will go out, they'll be no good, they'll get sent back, they'll get a refusal, they'll lose the customer, and you're going to be out of business. Is anybody familiar with a bottle? Okay, and we know what do we have? We have a thread. Right? We have a thread. We have another gazinda. This goes into that. For years, we developed, many years ago, we developed a product that would have a bottle, that was very important. The features are how long is that thread? What's the diameter of the thread? What's the root diameter? In other words, the small diameter of the thread. What's the distance from thread to thread? Because if it's not right, this don't go on. If it haven't happened, where it's a hard time? If it haven't happened, no, it doesn't happen. Anybody else have it happen? It happens. No, right? It doesn't go on. Why? Because there's either something wrong with this, or there's something wrong with that. Typically, it's that. So we had a machine, which, as the bottles went by, would, with a camera, pick up all those data points, put it onto a format. Back then, we had high pixel rates. We were able to now define the pixels and define each pixel size and dimensionalize the bottle as it went by. Because these are molded. This is not precision made. And those molds can wear after a while, okay? Where they can get gummed up, or the temperature of the material wasn't flowing right, okay? There's a whole bunch of things that go wrong. The world is made of rubber. I bring up this puppy because I like to drink the water. We had I'm gonna go back to some measurements, because this I find interesting, and I see somebody was the professor. Hello, professor. Are you liking this? Can I be a professor here?
Yes.
All right, thank you. The problem is I'm not getting paid for this. This is the problem. Okay, so we stopped at 3,000, right? We're gonna go on from there. This is where we call it a tenth. Remember we're calling a tenth up here? And I said, no, it's 100,000s. This we call a tenth in the manufacturing world because it is 1/10,000th This is 100,000ths, 10,000ths, 1,000ths, 1/10,000th. This is a tenth of this. So this is 1/10 of this. Let's go one more step. After a tenth, and believe me, we say, what are you talking about? Come on, Rich, you're talking silliness here. We're only zeros. If that's a tenth, we're going to make that 10 times smaller. That's 10 millionths. Let's go one more step. That is 1/millionth of an inch. 1 micron. 1/millionth of an inch. 1/millionth of an inch. 1,000,000 of those to make 1 inch. 1,000,000 of them. How big is a virus? Anybody know how big a virus is? Anybody know the dimension of the coronavirus?
5 microns.
Oh. 5 microns you could drive a truck through.
10 millimeters?
Huh?
10 millimeters?
Well, it is, we're gonna go down, it's about 2, 3, 4, 5, 3. Just a tad bigger than 1/millionth of an inch. He's got an MP, is that a 95 you're wearing? The mask you're wearing is a 95? You.
No, it's just small.
I hate to tell you. If this is this big, how are you stopping it? You better wear 5 masks. And that's why I found you need a mask. Oh, you need 2 masks. Then you need 3 masks and your head in the toilet. Kept on going on, right? Because we came to the realization that this is an itsy bitsy tiny thing. It's a little bit bigger than a millionth of an inch. And we're stopping it with paper. Hello? Didn't make sense. And so finally they said it didn't make sense. I don't mean to pick you out because I don't mean to make a thing out of it. I just want to make you realize that that's what you're dealing with, okay? You feel comfortable, you do it. But don't fool yourself. This is going to get you, right? This is going to get you. Because it's minuscule, all right? And how did I find out? How did I start thinking about this? I spelled something. I said, and I had my mask on. I said, how am I spelling it? I mean, what I was spelling is molecules of what was cooking. But those are big. Wait a minute. If I could spell it through this mask, then the virus can get me. Because the molecules went through the mask and they're 100 times bigger than the virus. And they said I was a fool. So was I a fool to you? Ah, good. He thinks I'm a fool. I'm sorry. All right, so now we're down to millionths of an inch. And believe it or not, we sell instrumentation that measures down to millionths of an inch. You can't do it in a regular environment. You have to have a vibration-free environment. You have to have a laboratory at 68 degrees, and it has to be temperature, humidity, and vibration controlled. But you can get measurements down in that range. Now, what do we use to measure? Sometimes we're using mechanical devices. Sometimes we're using lasers. Sometimes we're using microscopes. Right now, we're starting to use things that were in the medical business. For example, we are using CAT scans today in manufacturing to take parts and dissect them into sections just like you would on the human body with a CAT scan. It's X-ray after X-ray after X-ray, and it's knit together like we do with software with the human body. Way before ultrasonics became used medically, we used ultrasonics to make measurements and to look for inclusions. What does that mean? You're sending out light, you're sending out sound, ultrasonic sound, which you shouldn't be hearing unless you're a dog. Any dogs in here? Anybody ever hear an ultrasonic sound? I used to hear ultrasonic sounds. I really did. There used to be in lots of department stores ultrasonic systems for their alarms. And I would go into some department stores and I couldn't stand it. My wife would say, what's the matter? I can't stand it. I hear the ultrasonics. She said, are you a dog? I said, just pet me and let me go. So, ultrasonic sends out sound waves. Those sound waves hit the other side of the part. They bounce back. And the time that it went to get through it and get back again, we time it, we don't have figures. How fast does sound travel? And it changes. But in a vacuum, it'll travel, doesn't travel at all. It can't travel in a vacuum. Sound needs what? Vibration. Right? That's why they say, if a tree falls in the woods, does it make a sound? Anybody hear that riddle? Well, I say, only if somebody's there to hear it. Right? It has the potential for sound. But sound is actually in the world of the recipient. Right? So, it goes through a medium. In this case, it could be a piece of metal, generally. And it comes back. In that time, what was the time it went to get there and back is measurable. And we did that with ultrasonics 30 years ago, before anybody heard of using it in the medical world. Or if you wanted to inspect a pipe or something to see whether there was a bubble in the wall, you hit with ultrasonics, and you'd get a signal on an oscilloscope, okay, that there was something happening halfway in. Maybe you didn't know exactly what it was, but you knew there was a problem. Because the sound would get disrupted in its return, right, just like radar. How does radar work? Anybody know how radar works? Nobody knows how radar works? Radio signal.
I thought they said it like down, bounces off.
Right, there you go. Angle of incidence, angle of reflection. You send up a beam, and it could, in this case it was radio frequencies, and then it bounces back, and you have receivers, right? And you can see that there's something interfering with the radio frequency. That's why they started dropping in World War II, out of the airplanes, they would drop what? Aluminum flakes. So that when the radar hit the aluminum flakes, it would disperse, and you'd get a very weak back signal, and therefore they say, well, there's no airplane there. So it was getting the strong signal that was important. But if you had the aluminum flakes, okay, all over the place, the sound wave, the radio waves would get reflected in crazy different directions, and you get a very weak signal back. You say, well, it's a cloud. Right? Interesting, huh? You never know what you could learn from a guy from New York City. Do I look like a guy from New York City to you? Huh?
Yeah.
Tell the truth.
Somebody said it, yeah.
Yeah, why? Because I'm handsome?
Yes.
All right, that's right. All right, so we use lasers, we use light, we use electronics. We're going to go to another part of metrology. If you're bored, raise your hand. Everybody bored? You're not bored?
No.
Well, I'm getting bored. Now, what do you think of that? Now what? I'm going to take this off. Everybody gets the idea?
Yeah.
All right? You get the idea, you can get down to the nits here. You get the idea that you can do, George, put it off the screen, that you can close the loop between manufacturing and design and inspection and then going back and keeping, this is what they call this lights out manufacturing sometimes, okay? You can have a facility with nobody there, robots loading and unloading parts onto machines, parts going on to measuring machines that are being inspected, and the data being fed back to the machine tool in order to make the corrections. Data being collected statistically and being sent back to the CAD department so the design review can be made. The whole idea is to go for a perfect world. A perfect world. Never happened, but that's the idea. There are so many parameters to metrology. Of course, you know the electronic ones. I've been dealing mostly with the mechanical ones here, okay? I'm just going to go a step into something of interest, because people know about knees, prosthetic knees. People are getting knees, they're getting hips, okay? There's a big company that makes them in Jersey, and we do big business with them. They're called Stryker. Okay? And they make knees and hips and shoulders and ankles, okay? These are joints. So we don't have a gazinda, but we have things that are touching each other and working with each other. In a knee, you have a ball and a cup. Okay? You got a ball and a cup. What if the ball, I mean, that's a lousy ball, but let's say no, was like that, and the cup was like that? How good is that knee going to be? This gets into your bone, by the way. They drill into your bone deeply, and then they hammer into place. You got it? Does it feel good? They hammer into place the ball, and then they do the other side for the cup, right? And there's blood all over. This is a terrible thing to watch. But within a week, you're walking around. That's almost an amazing thing. You're walking around. They just destroyed your whole body, and you're walking around. But why does this work? Because this sphere is a sphere. And the sphere has something called spherosity. Now you gotta say that without spitting, right? Spherosity. What do I mean by sphericity? It's how round is round, how circular is circular. And it's got to be pretty perfect. Pretty perfect. And the same thing here. These forms have to work in conjunction with each other. If one is rough, and one is soft, and one is hard, and one is rippled, how long is that thing gonna last? So something as, and we probably have people in our family who have gone and had knees or hips or what have you, right? It's not an uncommon thing today. Could you imagine what it would be like if it wasn't all measured very, very precisely? Anybody know what a phonograph is? A phonograph? No? No? You know what a phonograph is? You know what a phonograph is?
Phonograph?
Phonograph.
Yeah.
Right. Edison. You heard of Edison? Thomas Edison? He invented a lot of things. One of the things he invented was phonograph. But when I tell you what it is, you'll know. Okay? They have a record with grooves in it, and it goes around like this, and it plays music. Okay? And when you go to nightclubs, they do the, you know, whatever the heck they do there with their, what's that called? Scratching them around, whatever the heck they're doing. But they're taking records. They're not doing this with electronically. They're doing it by hand, and they're taking the sound from these records. Okay, you ever see a record? You ever see one? Okay, so what is it? By the way, I think I'm taking all these things with me home. I'll bet. So this record has hundreds of grooves, right? And there's something that's writing in those grooves. Anybody ever take a look what the groove looks like? If you looked at the groove, it looks like this. Right? There's data in the groove. There's data in these grooves. How does that data translate from grooves to sound? Magic. No, it's not magic. But it could be magical in some sense. How does it happen? What happens is, in the world of phonographs, it had a diamond tip. And this diamond tip had a radius of 1/10,000th of an inch. Ooh. So we can get in and out of these grooves as the record goes around. And then it gets deflected. This now moves up and down with the grooves, okay? And then it comes to something you all know. You ready? A piezo crystal. Does anybody know what a piezo crystal is? Your engineering, electrical engineering guys? We don't know what a piezo crystal is? Tell me you know it.
Generates electricity in under pressure.
Right. It takes mechanical and turns it into electrical. It also does the other way. Electrical turns to mechanical. Right? 24, right? Bulova made the first watch utilizing a piezo. And that tuning fork is what made the thing go around. Anyway, this piezo, it's called a piezo electrical transducer, PET. It's an electronic thing, okay? And what happens with a piezo is if you hit it with a hammer on one end, you get electrical energy out the other. Okay? So it's taking now, you wouldn't hit it with a hammer, but I'm making a broad-based statement. If you mechanically twist it or put pressure on it in one way, out comes an electric output. Okay? Is that about right? Okay. So what the phonograph did was, this movement, mechanical movement, went to a piezo, which then output electrical energy, and that electrical energy went to something called an amplifier, And then that amplifier went to something called a speaker. Right? Simple enough. Of course, we don't use that anymore. There, I guess, did I, oh, there it is. We don't use these things anymore, but the concept is what I want to talk about. Why? Because I'm going to go back to the hip. All right? I'm going to go back to the hip. We have devices that have minuscule radii, 1/10 of a thousandth, that goes into a surface, goes onto a surface, and surfaces look like this. And we have devices that scan it with a small radius, goes into a transducer, they're not piezo's anymore. Goes into a transducer, electrical transducer. And that goes out to an output. That output could be an analog meter. Right? Once I get electrical data, I can do anything with it. I can do anything with it. I can print with it. I can do anything with it. But why am I showing that picture? Because this has embedded on it surface texture, surface finish, and that surface texture and that surface finish makes that either work or not work. You have a piston, I don't know what a piston is in a car, right? You have a cylinder and you have a piston. Piston goes up and down. Cylinder stands still. I mean, I probably can have a car, but piston goes up and down. Cylinder goes up and down, piston stands still, that won't work. But anyway. They make the pistons smaller than the cylinders. Otherwise, you couldn't get it. You would have a gazinda, right? But they also make them so that they're smooth. Otherwise, you'll get chatter. If you have a rough surface like this against another rough surface, this is, let's say, the piston. The piston, P for piston, and then we have another surface over here, and we call this the cylinder, okay? When these two things get together, they're gonna chatter like crazy. So what do? They look for technical advantage. And what they do is they make surfaces that look like that. Surfaces that look like that. Why? Because now you have these flats, okay? This is not a good one. You see, this should not have passed inspection, right? The quality of this is not up to my standards, okay? Just want to let you know that. If I ever come back, I don't want to see that, all right? And I want to see this on my surface. And I want to see this on my surface. Why? Because in an automobile, you want this to store the oil, while this is going against the other surface. Ooh. So too smooth, it's not good. Right? Otherwise, you don't have the pockets for the oil. All right. Suffice to say, I've done this for 55 minutes. Right? It seems like 3 years. I think Jesus said that. But anyway, this, so far, I'm thinking about at the end of this, but I don't want to be at the end of your imagination or at the end of your self-education, right? This is an introduction to metrology, an introduction to what's out there that you really didn't think about, and about how you think about things, and how measurement affects you every day in every part of your life. That's what I want to get into today. If I got that, I've done the right thing. Who has a question? Get out of here. Ah! Why don't you, yeah, you can go to bed. Go ahead. Oh, no, all right.
Okay.
What's the question?
So, which products is this company the most known for selling?
For what?
For selling.
For selling?
Yeah.
Oh, which are the most popular items that we sell?
Yeah.
Okay. From a standpoint of volume, the less expensive handheld gauging and stuff like that sells the most because they're inexpensive. They could be used by many people in the shop and what have you. But that's changing because people are going away from hand-applied stuff and they want to go to products that will make measurements quickly and more accurately. Okay? So it definitely, it's the smaller, lower cost handheld gauging products. But it's changing into the coordinate measure machines and some of the more sophisticated stuff. Any question? Somebody else? Did you raise your hand? Don't lie. Okay, you did.
I should say, where did the idea that this whole company stemmed from?
Where did the idea of this company come from?
Stemmed from, yeah.
I mean, when I started this company?
What influenced it?
What influenced me?
Yeah.
I'm trying to think, was I drunk that weekend? Let me think. It's a very good question. You're making me think, because I started this 50 some odd years ago, okay? I was a young guy, just as handsome as I am now, okay? But I came out of college. Oh, you want to hear my background? This is the truth.
Now you got him. He loves talking about himself. Now he really- That's it. He got another hour.
I went to college for 1 year, and I was asked to leave because I was a bad boy. Okay, I didn't do any work because I thought I was smarter than everybody else. This can happen when you're 18 years old. So I never went back. I went back at night, and I got about 2 years worth of college. That time I spent in college, the amount of engineering courses I took was zero. Not one bit of an engineering course I've ever had. But just as I taught myself how to speak Italian by putting a dictionary next to my bed and reading it night after night and picking up words, I also taught myself this science by being around people who are more knowledgeable and being in the manufacturing world and being application driven and being market driven and being personally driven. So then I came out of college looking for a job, and the guy said to me, it was a personnel agent, he says, "You are a sales guy." I said, "I am." So he sent me to a company that sold steel garbage cans. Wheeling steel garbage can from Wheeling, West Virginia. And I walked in there and I saw these desk upon desk upon desk of these guys on the phone getting orders for garbage cans. And I walked out and I said, "This is not for me." And then he sent me to another place, interestingly enough, that was the Eastern division of a company in Minnesota that made measuring equipment. And I really got interested in measuring equipment. And in the back, there was an old German toolmaker making microscopes and gear testers. And he had a machine shop back there. And he taught me how to make parts on the machines. Right? And he taught me everything he knew about measurement and everything he knew about manufacturing. And I was his protege. So at 18, 19 years old, I was getting an education right at the ground level from a German toolmaker who knew it all. And so I found it interesting. And then I founded this company some years later where I got jobs selling these kinds of things. And the rest is history until I got this. This is the high point of my career. I'm at Sacred Heart University. I mean, is there any place to go from here? Right? This is it. So that's the answer. The answer is, I have a much more varied background than you might have guessed. You might have guessed that maybe I had an engineering degree or something. You might have thought that. I mean, I sound like that too.
Yeah.
I'm a good boy.
Yeah.
But I've taught engineers how to measure, what measure is all about, statistical analysis, applying it into the production world, okay? And where is it all going? I've been doing this for 50 years. Bill Gates doesn't have a college education, right? He's got a lot more money than me, all right? So, not that I'm dissuading you from a great college education and you're gonna get one here, but my point is that you, not only do you have to have a college education, but you gotta have the will and the fortitude and the energy and the love of what you're doing to be successful. What do you think? Is that a good formula?
Sounds good.
Sounds good to him? The hell is he know? He thinks he knows it. He's probably, if he agrees with me, he's a very smart guy, all right? But that's what it's all about. That's what life is all about. Is having that application of life and putting your energy, your time, and your goodwill into it. And I'm here because of the goodwill. I'm here because I like the idea of talking to young people. And I like the idea of people hearing what I have to say, because my wife doesn't listen. That's it. I can't help it. All right? I wanted to have all girls, so look what I got. I mean, nothing I can do about it. Any other questions?
Yes.
Yes, Professor.
Can you tell us a little bit about the financial aspect of what you do?
The financial aspect.
Yeah, how good is it?